Okay, I'll try again. Make sure I push all the right buttons to get going here. So, again, we'll be I'll be watching a video about cosmology and redshift, and well, I'm going to be talking about gravitational pull or gravitational fields or whatever. The amount of gravity, but it doesn't seem like they consider at all the amount of gravity whenever they're talking about these things. And anyways, when you watch a video, just see if you can remember everything I've said in the past, or if not, just maybe I'll try to reiterate some of the points and see if they really understand fully what's happening when they look into outer space, because they have a lot of questions and things that don't make sense. Hello, Sea Science. How you doing? I got to make another attempt at a video because I already messed one up this morning. So here we go. I got to be sure to push this button here before I go. And hopefully I can... Actually, I need a separate window. I don't know. Can I do a separate window? I'll do a separate window. Okay. New tab to the right. No. Move to new window. Move tab to new window. That's what I need here. Okay. Now, hopefully, let me see if I can go like this. If I can move it over a little bit. Now, if you don't mind me doing this, very good. Big Bang cosmology in jeopardy, absolutely. And this is what they're trying to figure out. Oops, that doesn't work. Try this again. All right, let's go ahead and go with it. Everything should be good. Yeah, let's go. Let's see. I can do... All right, let me see. I got my StreamYard right there. Okay. I make sure everything's working right. No, I just lost the other one. Well, oh, there we go. Okay. All right. Without wasting any more time, let's get into it.
But I want to open that up more to these bigger questions that we've been talking about lately: black holes, space-time, some of these concepts that are really tricky to wrestle with and are extremely interesting, but seem to be lacking and full of mystery. And so if you want to address any of those topics, I'm going to put a final pin in our story of galaxies today with some of the least understood phenomena, which gets us back into black holes. But we're going to be talking about active galactic nuclei today, which are a special case of galaxies that seem to have something really, really energetic happening at their center. And the reason that we wrapped last time with the Hubble expansion and that we're not continuing with that immediately is because the story of active galactic nuclei and the interpretation of where they're located and what they are is largely dependent on interpreting the redshift of these constellations of bodies or whatever the heck is going on, right? The redshift of these galaxies associated with these active galactic nuclei. So we need to take a break and talk about these very strange anomalous redshifts.
Okay, now he's going to be talking about the redshift, but the redshift is being associated, of course, with the expansion of the universe. The only problem is it's extremely redshifted, and we have to keep in mind that he's talking about quasars, which is light from the very center of the galaxy, the very center of the galaxy, which is going to be extremely redshifted because of the amount of gravity from where the light is coming from. But anyways, keep that in mind.
Shifted objects, which we call quasars. Now, quasars, turns out, are going to be a central part of our discussion today. So let me just real quick review what we'll talk about. We'll talk about quasars, which are a special case of active galactic nuclei. Let's just call them AGNs. It's a real mouthful calling them by their full name. And I want to talk about some potential hypothetical mechanisms that could underpin them. Now, of course, the possibility remains at the end of the day that the reason that we see these very strange and extraordinarily energetic and bright phenomena at the center of these galaxies is because, well, physics breaks down and reality stops making sense. There's this rip in space-time and we have a
Okay, physics doesn't break down. It's exactly what gravity would predict that is happening, including the redshift, including these excessive speeds that you see in away from the center of the galaxy and everything. It's gravity that accounts for everything.
Supermassive black hole. But there might be some other possibilities, some of them more mundane, some of them perhaps even more tantalizing. We're going to talk about it's hard to talk. We're going to talk about galactic magnetic fields at the end, which is something I've been studying a lot lately and talking to some astronomers down at Stanford that are working on this. And it's a brand new science, which is really interesting. So what I'd like you to do in your response is consider some.
And magnetic fields, or what they call electric universe, has been a big thing in the past. The only thing is that it doesn't have that much effect on large bodies. It's more gravity, which is, some people say, is the same thing as magnetism anyway, but which is another rabbit hole. But anyways, but it's gravity that does most of the effect.
Some of these alternative processes. As we're reformatting this course for next year, a big portion of the program is going to be about considering alternative hypotheses to what is the standard narrative in the textbook, because this is like the really creative element that seems to be sort of bleeding out of science right now. And I want to find a way to get you guys, when you're young and just starting off on your careers, maybe a few of you will become scientists. I want you to start exercising that muscle in your brain that allows you to think of creative solutions to problems, even if you're wrong. So the idea is to think about all of the possibilities that could explain these phenomena. Maybe some of them are good, maybe some of them are bad, but we need to generate some ideas. Otherwise, we have to accept that physics just stops working at some point, and make up your own mind about that. But it's a little.
And no, physics doesn't stop working. It's exactly what general relativity predicts.
Untenable for me. So let's look at this special case. I'm going to try to keep this as brief as I possibly can in order to get us caught up so that we can continue next Thursday. But it all comes down to the fact that there's something really strange happening at the center of certain galaxies. So what's going on? Now, the discovery initially came with these phenomena, which they dubbed quasi-stellar radio sources. This is where you get the contraction quasar from. Basically just means something sort of like stars, but not quite like stars. Now, this happened right after World War II because, of course, all these radio technologies were coming online, mainly to fight the war, but the astronomers started using them as well. And they noticed that some of the radio sources were in the same location as these really faint blue stars, and no kind of star that anyone knew about in our galaxy would emit such powerful radio frequencies. So they obtained the spectra from these faint blue stars, which had, somewhat common emission spectra, namely the Balmer series that we talked about at the beginning of the lecture series. But there was something strange about the spacing of the Balmer series. It seemed like all of the lines were shifted really far to the red. Now, if you just attributed that to a recession velocity, right, that this galaxy or whatever it was, or this quasi-stellar object was moving away from us really fast, it boggled the mind how.
Which makes no sense at all that the center of the galaxy would be moving away faster than the galaxy itself, and it's just, makes no sense.
How that could be possible, because it was moving at some very significant fraction of the speed of light, and that's problematic because accelerating material that fast is almost energetically unimaginable, especially to the people first studying these. So these objects that appeared star-like but had this really strong radio emission was then joined with another set of objects that also had this really star-like appearance, these high redshifts, but also no radio emissions. So they kind of grouped these all together and they started examining them in other bands, infrared, X-ray, and called them as a class these quasi-stellar objects, so quasars, QSOs. If we take a look at some of these things, we see that, well, they look a lot like stars at first glance. You can see on the screen, we've got a picture from the Hubble Space Telescope. And it's thought that one of these two bright quasi-stars in the middle is actually in our galaxy, but the other two are 9 billion light years away. And we'll talk about how they come up with these distances in a little bit, because that's actually really critical to this discussion. Now, all the spectra in these quasi-stellar objects show redshifts, and none of them ever show blue shifts, which is really interesting. Because what it turns out is that the quasars are associated with some sort of emission from the center of these really active galactic nuclei, right? The center of galaxies. But quasars turned out to be the particular name that we gave to the ones that were pointed right at us, so we could get a nice view of them. Which is strange because, we're going to start looking at the fact that these active galactic nuclei emit these really powerful jets of radiation. And these jets, though they're pointed directly at us, still appear to be redshifted, which is really strange because if they're emitting a lot of particles and subatomic materials and whatever directly at us, well, we would think that it's coming towards us, it would be blue shifted, but that's not the case. So this.
Okay, he's thinking that the light that's being emitted from these plasma jets are coming in our direction, so they should be blue shifted, but it's coming from an extreme gravitational well, which is the reason why it's red shifted, because of the amount of gravity from where it's being emitted from. And that's the reason for the redshift. It's the amount of gravity. Gravity as it leaves the galaxy is redshifted. When it enters the galaxy is blue shifted. Now he's thinking, well, if it's coming our direction, it should be blue shifted, but it's still redshifted. And but that's because of these the source, the origin of where it's coming from is the extreme gravitational well, and that's why it's redshifted.
Starts to cloud the discussion of where these things are, where they're located, right? Because if you think back to our last lecture, we were considering the distance ladder, and we said that if you want to find the distance to something relatively nearby, you can use a pretty standard parallax method, right? You can use these binary systems to set up some sort of triangulation and get a pretty good estimate of the distance to that binary system. And that's really as far as it goes with direct observations. Beyond that, you start having to use these things called standard candles, right? You need to start making assumptions about what kind of object you're looking at. Is it a giant mag light, or is it just a birthday candle? And if you know which it is, and you know how bright it is, then you can estimate exactly how far away it is. Now, this gets compounded even further because at some point, we're not able to see these nice supernova. We're not able to see these nice Cepheid variables that can give us this hopefully reliable standard candle to get that distance estimate. We're actually looking at the Hubble relationship. That is, that things that are far away have high redshift, and we're converting that into distance. So you see a high redshift, you think that's far away. And these are some of the brightest objects. These quasars are some of the brightest phenomena in the sky, right? But they're also really high redshifted. So we think this is an interesting contradiction of terms. Normally when we see something bright, we think it's close by. But then we have this Hubble relationship where things that are far away must be redshifted. So we have bright things that are highly redshifted. And it creates a real conundrum because you're talking about an energetic process that is far beyond the scope of anything that we see happening.
So, so it thinks that just because it's redshifted, it's moving away from us. The only thing is that these quasars, they're extremely redshifted, way more than what they should be, approaching the speed of light, which takes a lot of energy, which is just nonsensical because there's no energy, there's no dark energy to do that, which they think it is, but they think that the vacuum energy is the dark energy, but the vacuum is the opposite of the dark energy. Vacuum energy is because of all the space-time that's going into all the black holes around the universe, which causes the vacuum energy, which is not an inflation, it's not an expansion, but they want to equate it with the expansion of the universe or the inflation of the universe, which is not even happening. The redshift is caused by the amount of gravity out there that the light has to travel through to reach us. The farther away it is, the more mass that it has to pass or come through, or gravity has to come through to reach us. And not that there's a whole lot, but it's enough to redshift it. Like, as you know, the farther away it is, the more objects that there are out there that will redshift the light. But these quasars, quasi-stellar objects, are extremely redshifted, much more than the galaxy that they're even coming for. So it makes no sense at all. But they're still trying to say the universe is inflating or something. I don't know.
In our local part of the universe here in our galaxy, it's just an unimaginable feat for something to be so bright and so far away. And the hinge of that comes down to the question of how far away are these things really? Because, of course, some components of the redshift may very well be attributed to their distance in this whole Hubble landscape, the Hubble redshift landscape. But there seems to be some component of intrinsic redshift which clouds the discussion a little bit. And we'll see more and more of that as we go forward. So some of these redshifts, by the way, if you just attributed them to recession velocity, so how far it's moving away, we're talking about velocities somewhere in the neighborhood of 96% the speed of light. And that's just almost unimaginable. Remember that if you accelerate something,
right, 96% of the speed of light is just total nonsense because it takes energy, which is going to explain right now.
you need an energy that's proportional to that. And as you approach the speed of light, you need an unending amount of energy essentially to move something past the speed of light. It seems to be the limit by which those materials can actually be dislocated from what
you can't move it past the speed of light. That's just not possible. It might appear to be moving faster than the speed of light because you're not using the correct measures of time and distance. You're using our measures of time and distance, looking at something out there that's moving faster than the speed of light, but it's really not moving faster than the speed of light. It's just that the measures of time and distance aren't the same as what our measures are here on Earth because of gravity inside the galaxy.
Whatever gravitational web they're locked into. I think that a reasonable analogy is thinking about it as the actual deformation of that medium that they're all embedded in, right? So if you want to use space-time, that's fine, but you're talking about it has a stiffness to it, right? Whatever is holding atoms to one another, and whether it's just structures from the atom themselves, it doesn't matter. There's some deformability of that, which is limited. If I slam my hand down on the table right now, there's a wave of deformation that's going to travel through the table to the other end of the table. It has a speed limit to it, right? The atoms in the table can only deform and get out of their lattice position so fast, right? The same is true with the air. When I'm making sound, it's hitting the microphone right now. The air can only relocate itself and host those waves in a particular fashion which is commensurate with material properties of the air molecules themselves. So something is causing us in the universe to experience this absolute limit by which something can move. And what's really crazy is that these redshifts, if they're just Doppler recession velocities, are something approaching the speed of light. So that seems untenable. There must be something else going on. And I'm sorry if this is somewhat confusing because...
Yeah, there is something else going on, and it's called gravity, because when light leaves a galaxy, it's redshifted because it's coming out of the gravitational source. When it comes into our galaxy, it's blue shifted because it's coming into a gravitational source. That's what's causing the redshift to begin with. So a more massive galaxy to begin with is going to be more redshift to start out. Less massive is going to be more blue shifted. But they think, well, it's moving towards us. Maybe it is a little bit, but I don't think it makes a whole lot of difference how fast it's coming toward us. It has more to do with gravity than it does anything else. And especially these quasars, which comes from a deep, deep gravitational well that makes them extremely redshifted, which, according to him, it must be moving 96% the speed of light, which is total nonsense.
We really want to be able to say something certain, right? We'd really love to say that every time you see a redshift, it's a recession velocity, or every time you see a redshift, it's an expansion coefficient, right? For the actual distance between objects in mass for the universe getting bigger, right? This is the idea from Lemaitre and the Big Bang, that everything's just kind of moving away from it, from some central point. But neither one of these seem to account for it perfectly. So even if you go with some combination of the two for this redshift, you have a lot of freedom in which one you have to accept, because you need to see that there's some limit as to how fast these actual bodies can move, that these particles, these really high energy nuclei that are being ejected from the center of these galaxies, how fast can they really move? So something else is going on, and we're going to try to get to the bottom of that. I hope that we can get closer to an answer for it, but I'm afraid there's no simple solution that has been proposed yet, other than, of course, supermassive black holes, which essentially amounts to physics stops working at some point at the center of the galaxy.
All these pictures here that he's shown so far from the Hubble telescope, they all have 4 points on the stars. The James Webb telescope has 6 points, 6-pointed stars, because the way the telescope is designed or made. But anyways, I don't even know if it gets into James Webb observations, and I don't even know if we can watch the video that far. But anyways, we'll just go ahead and try to see how far we get.
So, people first started looking at these and asked questions about whether quasars obeyed Hubble's law, and that those really large distances were actually implied by the redshifts. And we see some examples here. So top left shows a quasar that's at the heart of a spiral galaxy that's about 1.4 billion light years from Earth. Bottom left shows another one that's in an elliptical galaxy some 1.5 billion light years from us. In the middle shows some remote pairs of interacting galaxies. One of them harbors a quasar. And people started studying these, and one of the first people to really point out that there might be some problems with this Hubble estimation of the distance of these quasars was this guy who was actually one of Hubble's students, a very precocious young student, very smart and very much a go-getter. And he ended up kind of making himself a bit of a persona non grata in the institutions he was working at, because he started cataloging these quasars. And he created what he called an atlas of peculiar galaxies in 1966. And what he found initially was that a lot of these things we were calling quasars seemed to be linked by trails of dust and so forth to nearby galaxies close to us. So I guess it's worth mentioning at this point that most of the quasars that we're talking about are really far away. And this brings up the question, why don't we see any nearby us? And are the quasars actually close to the galaxies that we associate them with? And Harp seemed to think that there was reason to believe that they weren't necessarily spatially locked to the galaxies that we had been deeming them associated with. In other words, the quasars might appear at some distance, right? If there's a jet at the center of the galaxy, that quasars could be
Shalom, Brother Timothy. How are you doing?
mistaken for being at the galaxy if they overlaid it in some way, right? So if the jet was interacting and there was some energetic process happening in front of the galaxy, that you would mistake it for being.
Yeah, so what he's talking about now is whether or not the quasar is actually associated with the galaxy that it looks like it's coming from. So, and the problem is, you'll get into that the quasar is much more redshifted than the galaxy that it's being, that it's coming from, that the light's being emitted from. So there's a problem. How can the center of the galaxy be moving farther away faster than the galaxy itself? And then they got some funny explanations for that. But anyways,
Part of the galaxy that was behind it. Now, he kept looking at these, and he found that there was often very high redshift quasar activity that was very different redshift than the galaxy that we were associating it with. So this contributed to his suspicion that this redshift wasn't actually something that we could truly associate with the Hubble relationship or with velocities per se. There was something else going on that was causing the spectra of these atoms, right, that we're looking at, the vibrations, the light spectra, to be shifted red that had maybe nothing to do with this beautiful distance relationship or
yeah, there's something else going on, definitely.
this beautiful Doppler effect. Something else could be going on. Now, today, and of course, chemists know that chemistry often does alter the line spectra in very interesting ways, right? So when you actually recombine atoms or you rip them apart, you can actually get a modification of that atom such that its spectral frequency does shift in interesting and predictable ways. But this is, of course, work that's going on outside of astrophysics as far as I can tell. So,
unrelated to astrophysics. Thank you.
Now, if we do accept that the reason that these high redshifts are there with these quasars is because they're really far away, then there must be a truly impressive amount of energy that's going on at the center of these galaxies. If they're actually at the center of the galaxies and they're really, really bright, they're outshining the whole galaxy, they're making these galaxies look like they're right next door, but they're really, really far away according to the redshifts, then we have to consider something really crazy and super energetic must be going on. Now, if that isn't the case, and these are actually much closer, or the quasars are in some sense the really bright quasi-stellar business that we're seeing is ejected from these.
Of course, I hate repeating myself, but the extreme redshift from the quasar is because of the extreme gravitational well that is the source of where the light is coming from or being emitted. That's why it's more redshifted than the galaxy where it's supposed to be coming from. I mean, it's not complicated.
These galaxies, but actually quite close by to us, then we have a totally different program to be looking at. Now, there's been a number of papers published over the years that are in some sense taking holes in the standard model of quasars, which I want to be absolutely clear of, is that these galaxies themselves host the quasars, right? The quasars are at the center of the galaxies. But there's some problems with that. There seems to be some overdensity of redshifted quasars in the field around our nearby galaxies, right? So, in other words, these high redshift quasars seem to be aligned with one particular axis of the redshifted active galaxies. And there seems to be bridges of gas between the galaxies and the redshift galaxies. This is kind of similar to what Harp was arguing, that they're associated with galaxies that don't have the same redshift as them, right? That are perhaps more nearby. And this is problematic for lots of reasons because they're supposed to be of the same objects. This is one paper which I recommend you might check this out. It's called On Quasar Host Galaxies at Tests of Non-Cosmological Redshifts. Now, one possibility with that is that the host galaxies are actually in a transition, right? So we talked last time about how most standard cosmology imagines that the galaxies all formed at the same time and that they are not really we're not going to really see new galaxies forming at any moment. But one possibility that's creeping into the mind of people is that the quasars are actually some moment.
And another thing is they keep on trying to talk about the formation of galaxies, how they're formed and how they make star babies, and it's just they got so many stories that they tell, just trying to back up their worldview, their belief, that everything's natural when it's obviously not that. Nothing in the universe is 100% natural because nothing can make itself or order itself or direct itself.
moment in the evolution of galaxies. Now, of course, because of this redshift relationship, the thought is that, well, all these quasars are far away, therefore they're in the distant past. Therefore, yeah, quasars could be an important moment in the evolution of galaxies, but it's something that happened in the distant past only, right? So it reinforces the idea that there's a linear timeline to the universe, that it had a start, that it's progressing, and it eventually will end in some sort of cold death of everything. We're all going to be swallowed by black holes and so forth.
Which is not the case, that these extreme effect of quasars is because of matter interacting with the black hole. That's what causes these extreme bright lights that are like they have a beam they point like a flashlight, or the ones they're talking about are pointed straight at us.
But again, how reliable is that distance narrative, right? Another paper I wanted you guys to check out, if any of you are interested in following up on this. It's called Anomalies in the Counts of Low Redshift Quasars. This one points out an interesting point. There are some galaxies that actually appear to have some inherent blue shift alongside their redshift. So some of the different atoms, right, some of the different spectral lines, those particular frequencies are actually shifted towards the blue, which is really strange. And the thought is that this could in some sense be confusing the distance ladder as well. Now, most of the quasars with inherent red.
Again, the more blue shifted light is coming from parts of the galaxy that are not as much affected by the gravity, which also affects time and distance. And the effect of changing the time and distance is what makes it possible for us to see light from distant galaxies instantaneously, because there's no gravity between here and there. There's no matter or mass to slow down time or contract distance. So the distance isn't as far and the time passes by faster. That's why we can see distant galaxies within a 6,000-year-old universe.
Redshift, right? So ones that can't be ascribed to distance per se. So there are some quasars that are pretty close to us, and those have redshifts as well, but we can't possibly say that they are due to Hubble relationship or anything like that. So the authors of this paper are really putting out a call for people to study these quasars that are in this redshift range, right? This somewhat low redshift range, but still anomalous with respect to their distance. So people will use other methods with these nearby galaxies, some of the other more.
One thing he's not talking about is the size of the black hole, the size of the galaxy. They come in all different sizes. So obviously the larger ones are going to be more redshifted, and the ones we can see that are distant are the larger ones that we can see. So they're going to be more redshift to begin with. It all depends on the amount of gravity, which depends on the amount of matter or mass where the light is coming from.
Proximal sources on the distance ladder to gauge where these things are, and they see these intrinsic components. So the idea is we need to reach out into our imaginations and really pick at what could be the sources of intrinsic redshift. And I would suggest to you that chemistry may play an important role in that. There's also the discussion of galactic magnetic fields, which we'll get to at the end of this. And
Well, I was thinking chemistry might affect it, but I don't think so. Because it's, between here and there, there's not a lot of chemistry going on between here and there. There might be an argument to be made, but I don't think it's that much happening. Has more to do with the amount of gravity than anything else.
I'll hopefully have time to follow up more with that when we do our review at the beginning of class next Thursday. So the textbook goes through next how we can gauge the size of these objects. So this is actually quite interesting as well, because when we're talking about how energetic something is, in some sense we're talking about the density, right? So how much luminosity is happening in a certain region. And the way that they do this is they look at the difference in how long that light takes to travel from one side of this quasar to the other. And what they find, is that they're really small. So, I think that the distance estimates they come up with these, let me see if I have this written down here.
Yeah, no, what he's talking about is the size of the black hole is basically really small because of the contraction of time and distance. Contraction of distance means that it looks very small to us, even though it's very large. It'd be like Snoopy's doghouse. It looks small on the outside, but on the inside, it's very big. He's thinking.
The idea is that the quasars actually, the difference in the light traveling from the far side to the near side is something like a few light months, right? So not huge distances, right? Now, of course, we measure the size of the center of a galaxy on the order of light years, right? So how far is a light month? Well, Pluto takes something like 5.5 hours. Light, the light from Pluto takes something like 5.5 hours to reach us, and the nearest star is something like 4 light years away. So really, really small. So closer to on the order of within our solar system boundaries. I think that's a reasonable way of thinking about it. If you think about the edge of our solar system, like the Oort cloud, as being maybe a light year or two away, then we're talking about something really, really small. So a couple of light months for all of this brightness to be contained within this distance is extremely, extremely small and dense. All of this activity is happening in a very small place, according to this differential light path travel model.
Again, it's a very small place by our measures of distance, but it's really a lot bigger because the measures of distance are contracted so much that when things moving into that area look like they're stopped because of how slow they appear to be going, because they don't look like they're moving very far, but they are. It's just that they have a different measure of time and distance, which is much more contracted. And it looks small to us, but it's actually not as small as what it looks to us.
So really, really energetic. And of course, what's interesting is you also see these jets associated with it, right? You find these nuclei in these gases are moving actually within some percentage, some small, maybe 2% of the speed of light. So it's actually stuff.
Here you go. This is the one they were saying was moving 7 times the speed of light. They actually wrote a paper saying it was 7 times the speed of light. So what they did, these little clouds coming out, these puffs coming out of here, they measured them, the speed moving out, and they did the same thing with explosions where the clouds are supposedly moving faster than the speed of light too. But anyways, they measured the velocity of this thing according to our measures of distance, and they came up with it was going 7 times the speed of light, which is not possible. Because see how far away it is from the center? That's how far away it is from the center. So that's why, and a galaxy is where this light beam is here, but I mean this light source here, but you can almost see the measures of time and distance increasing in size. Of course, it would expand a little bit, but it's almost like you can actually see the increased measures of size as it moves away from the center. And I don't know. I don't know why they have such a problem with understanding that you can't project our measures of time and distance on here on this part of the galaxy because it's way from the center of the galaxy, which is much more expanded and a faster rate of time, which makes things go faster, makes everything go faster. When you look towards a black hole, it looks like it's going slow. When you see things moving away from the galaxy, it looks like they're going faster. Everything's going faster because they are going faster. It is going faster because it's a different measure of time and distance, which somehow they don't understand, I guess. I don't know. Anyway.
Being kicked out of the center of these galaxies emanating from these quasars. In at least some of the cases where this is not always seen. And of course, there's contradictions to this as well, right? Where you see that actually the jets and the redshift associated with where the jets are pointed at these galaxies is very different than the quasars themselves. Now, in order to find a common model for what's causing these quasars, we should probably review the characteristics of these things that we've been talking about so far. So they're really powerful. They emit more power and radiated light than all the stars in a galaxy combined, which is just completely bizarre. And of course, it's within a narrow distance window, right? Really, really small, something on the order of a solar system. Now, another thing to consider is that quasars are often observed to be shooting out these pairs of straight jets at close, at these almost light speeds in a tight beam.
Again, it looks like a small area because the measures of time and distance are contracted. That's why it looks so small. But if you were to go there, it wouldn't be so small. But to us, it looks very small because of there's more gravity there, which contracts distance more. Anyway.
Beam to distances that are far beyond the galaxies in which they originate. And these jets themselves are a really strong source of radio and gamma radiation. And because the quasars put up so much power in such a small region, they just really can't be conceived of as being powered by anything like stars, like nuclear fusion or fission or any of these processes that we've examined so far. There's nothing we can think of that would be that powerful in such a small unit of distance, right? Now, it's interesting. So at this point, the textbook makes this claim. It was only evidence of the existence of black holes that accumulated that it became clear that only supermassive black holes could account for the observed properties of quasars and AGNs. So this is interesting because we know that the biggest elliptical and spiral galaxies all have these nuclear bulges. There's a lot of stuff going on at the center. And when your textbook says that evidence of the existence of black holes accumulated, what they mean is that they can't think of a mechanism gravitationally by which all of that material would be swirling around the center at such incredibly high speeds. Remember, in our solar system, something like Mercury is going really, really fast compared to, well, something like Pluto, right? This is the traditional gravitational worldview for how things orbit. The problem is we know that galaxies don't obey this nice gravitational path. We know there must be something else going on, right? This is how we get into things like dark matter, right? It seems like...
Okay, so now he's talking about dark matter because it needs dark matter to form the galaxy in the first place. That's why they keep on holding on to dark matter, because they have to have dark matter to form the universe in the first place, because it won't form itself, because hydrogen doesn't coalesce by itself, and stars don't coalesce by themselves. So they come up with this dark matter to explain the movement of the outer spiral arms, because, like I said, everything, as you go away from the center of the galaxy, everything is moving faster. But they think that it's going too fast for the amount of gravity in the galaxy. And Fritz Zwicky, he said, he called it dunkle materie. Dunkle materie is dark matter. And it just stuck, and they keep calling it dark matter that's you can't see. But it's not because of matter you can't see. It's because of the matter that is there that drops off considerably. The farther you get out away from the center of the galaxy, the more the gravity drops off, which means the more the distance, the measure of distance is expanded. That's why everything looks bigger in the outer parts of the galaxy. Everything looks bigger because distance is expanded. And everything is faster because the rate of time is going faster. Now, if you have both the distance being expanded and the rate of time going faster, it's going to compound the effect of it going faster. Now, what happens is the tendency is for the stars in the outer parts of the galaxy, the tendency is for them to slow down and go really, really slow, like they do in our galaxy. I mean, like they do in our solar system. The outer planets are going really, really, really slow because they're really, really far away. So that's what they're saying, is that these stars that are far away from the center mass should be going really, really slow, but they're going faster than expected. But eventually the distance is going to make them go slower. So there's like a curve there of the speed. Even with the expanded time and distance, they're still going slower on the very, very outer edges. But that's because the tendency is to always go slower the farther away it is from the center mass. But these arms look like they're going faster because they are going faster, because time is sped up and the distance is expanded compared to the center of the galaxy, which he says is a really small place, but it's not really small. It looks small to us because we don't have those measures of time and distance. It looks very small to us. But if we were to go there, it would be large. And all these outer spiral arms would look even larger. Anyway, but they don't get it that this is not like looking at something in your yard. It's not like looking at a tree in the yard, because the more you move out to the edge of the galaxy, the more the measures of time and distance change. The faster the rate of time is, the farther you get away from the center, and the larger the measure of distance is. So things don't appear to be as far away. That's why you have a spiral going down to the center, and the center is really small because the measures of time and distance are small. It's like everything can be explained just by gravity alone, but they're not even considering the measures of time and distance changing when they look at it. Because it's not like looking at a cat or a dog in the yard. If it was a cat or dog in the yard, it'd be real skinny in the middle, and then the head and the feet and the tail would be very, very large, and would be moving around really fast, 7 times the speed of light. Yeah, or faster than the speed of light. But which is not the case. It's just that the measures of time and distance change. That's all. That's all it is.
Like there's something else happening. Now, it could be that
there's something else happening. I just explained it. Yes, there's something else happening. It's the changing amount of gravity changes the measures of time and distance. That's what's happening.
Really an exotic form of material that we can't detect. This could be represented by dark matter. It could be a really cold, mundane kind of material, like a bunch of dead stars. There are a bunch of really cold old moons and planets. I mean, it'd have to be an extraordinary amount of them, right? Very cold, almost boggles the mind, given the 14 billion year given the 14 billion year birthday that we've set on our universe, how you could cool that much stuff off so quickly.
See, the 14 billion year universe, he's assuming that the universe has a single rate of time. And when time is never running, time is never the same because the amount of gravity is never the same everywhere in the universe. If you're out in between a galaxy and us, our galaxy, between two galaxies, the gravity of both the galaxies are pulling on each other, canceling each other out, means there's no gravity. That means that light traveling through that space is traveling instantaneously because there's nothing to slow it down and there's nothing to contract distance. Hello, this one guy. How you doing?
Quickly. Or it could be that there's something else besides gravity playing into the cohesion and rotational dynamics of galaxies. And I think that's a really intriguing possibility as well.
Again, electromagnetism is not going to have that much effect, which he already admitted. But if you take gravity alone, would explain it. If you're taking into account the changing measures of time and distance, which they never do, they never talk about it.
But if we assume that gravity is the only player here, then we are essentially left with some anomalous structure at the center of the galaxies. And that's essentially how we get to this idea that we must have an extraordinary amount of stuff crammed into an impossibly small space, right? And that's what we're looking at with the standard model for these quasars and active galactic nuclei. We're looking at an extraordinary gravitational source at the center, which is giving off, which is causing some sort of super energetic reactions to glow. Now, this is interesting though, because the black holes themselves, right, by definition, light can't escape from these things, right? So it can't be the black hole itself, even if we admit that these black holes, these rips in our understanding of physics, are an actual thing. It's like we know that by definition that light can't escape from. So the only possibility is that the stuff outside of this anomaly, outside the actual limit of the black hole, is causing all of these collisions of material and this swirling and ripping apart of stars and just crazy chaos to ensue. And that acceleration of all that material is actually what's glowing and leading to something that we see in the quasar. And I think this is actually quite compelling, that there is stuff moving really, really fast. We can actually tell that from radial velocity measurements. And it does appear to be super ionized. One way to counteract all of this would be to think of it as a superstar almost. And what you're seeing is the corona of that superstar. Now, the superstar is not and what I mean by superstar is really just a bunch of stars that are all just squished together. Now, if we treat stars like they're balls of gas, then of course, if you have that much gas in one place, it's going to collapse because ideal gases can collapse indefinitely, and you're going to get this physical anomaly called the black hole. But if stars actually do have a lattice structure, which kind of seems like they do from the continuous spectrum, right? They have that nice black body spectrum. If stars do have some sort of lattice, if they have a material basis that's not gaseous, something more liquid-like, at least at the photosphere, then you find yourself in a very different position where you can actually join a lot of these little droplets together, and you might be able to get something at the center of galaxies that is very much like a superstar. So, again, the only reason we don't think that there's...
Well, they have hello. Good morning, Jay. Anyway, See, I forgot what I was thinking of.
Superstars at
Oh
the center
yeah,
of
the
galaxies.
superstar. They have the liquid metallic hydrogen seems to be what the stars are made. I mean, that's what some of the planets are made of, liquid metallic hydrogen, but there's not enough of it to become a star, obviously. But what he's saying is if you got this liquid metallic hydrogen or drops of it, which is metallic and magnetic, swirling around the black hole, is making what appears to be like what he calls a superstar or a giant star, but which is not really a star. It's because it's a quasar. That's what a quasar is.
Is because all of these collisions would lead to mergers, and the mergers would lead to too much gas in one place, which would collapse. If the stars are made out of gas, then the most likely solution is that these active galactic nuclei are something like superstars. If you go back to our discussion of the formation of stars, you'll notice that when these stars are being formed, they also have these enormous jets. These protostars also have enormous jets that look very much similar to the jets coming out of these active galactic nuclei. So there might be something to that.
Recordings just got better. Hey, it's Dana from StreamYard. I'm so excited to announce that
StreamYard, I'm on StreamYard.
Now, the jets themselves aren't black body radiation. So we're actually talking about something analogous to the corona, right? The atmosphere of the sun, which is full of all this ionized material. The body of the sun itself does have this thermal heat spectrum, but that's not what we're talking about with these jets, right? He's
getting away from the top. He's just explaining how the light's coming from it. I don't even think I got this far in the video, but anyway, they just get everything wrong because they're not taking into account the measures of time and distance, which change the farther away you get from the center mass of the galaxy. It's just so simple. Anyways, and I might have to go to work pretty soon.
It's really an intriguing possibility that what we're seeing here, and here's a good picture of it, is that you have actual something that's...
Well, I guess I got to go to work now. So bye, everybody. Everybody take care. God bless everybody.